Okay, so today we're going to be talking about work and kinetic energy, which is basically just a way of talking about the motion of an object without talking directly about the forces. So it's knowing or the path of the motion. So knowing only the motion or only the initial and the final conditions, you can find the velocity, you can find a lot of other uh, material, or you can find a lot of other answers just knowing the velocity, just knowing the initial and final positions and what type of forces are acting on it rather than calculating the instantaneous force at any given time. So first, let's define work, where dW equals F dot dr equals, let me get this panel out of the way, or whatever, equals F, the magnitude of F, the magnitude of dr, cosine theta. If you remember, whatchamacallit, if you remember dot products from second week, I think, then this is just a dot product, and this tells you basically how much the work or the force that you're applying overlaps with the force that or the path that you're going along dr. So in FDR, if you're going directly along the path, so the force is pointing this way and then you're walking this way, then you have the maximum amount of force, FDR. But if you're walking along the path, a path opposite of it, then you get negative FDR. And if you're going at some angle with respect to the force, then you're just going to get F dot dr, which is F dr cosine theta. Uh, it's the projection of how much force is along the path that you're walking, the path that the object is moving. So one of the ways to actually talk about work is because this is a infinitesimal amount. This is dW instead of actual change in work. This is the infinitesimal change in work as you're talking about going along an infinitesimally short path. Then the actual work as you go from path A uh, to B is equal to the path from A to B F dot dr. And if you have any questions, of course, feel free to bring them up. I'm just kind of rambling to myself when I do these lectures usually, so it's really helpful to have somebody else here. So it's just the integral of that infinitesimal is going to give you the total work done. So what this means in practice is that we can calculate the work done, which is in units of kilograms meters per second squared times meters, which is in kilogram meters per second squared, which is a unit called a joule. So we can calculate the work done by friction, which is going to be something that's uh, always acting in the opposite direction of it's always acting in the opposite direction of the motion that you're going through. So work friction equals F kinetic dot dr, which is equal to negative F kinetic times the total distance that you go from A to B. So F kinetic times dr uh, is the distance that you go from along your path from A to B. So no matter what path you take, if you take a straight line, if you take a curvy line, if you go in a circle, then friction is going to do work which is keeping track of yeah, which is just going to keep track of uh the path that you're taking because it's always in the opposite direction of the path and it's always going to correspond directly to the opposite direction of the path. So it's just going to be negative fk times whatever path you take. So that is going to be defined as negative fk times the length of the path from A to B. And then the other useful thing that let's cordon these off. Let's like just make it so that this is on one side and this is on the other side. So the work due to friction is a useful thing, and that's actually one of the only works. It's called a non-conservative force because it's one of the only works that you're going to find that depends on the path you take rather than just the initial or the final position. So for one that just depends on the initial and final position, we talk about work of gravity, which is negative mgj dot dr, which is negative mg times j, the y direction, uh, times dy, because you only care about, or j, let me rephrase that because that still gives a direction. So you only care about how the forces, how the force corresponds to or overlaps with dr. So in this case, since the force is completely in the j direction, you only care about the distance traveled along dy. So this is equal to negative mg times yb minus ya, which is actually, let's be a little more explicit than that. Mgy from A to B is equal to negative mg yb minus ya. So as an example of this, you can talk about just lifting an object up how much work you can do by just straight up lifting an object. But the more interesting question is if you uh, take an object and transport it in a straight line along 4 meters in the x direction and 3 meters in the y direction for a total of 5 meters along the xy or along this straight path, then what you're going to do, what you're going to see when you look at the work isn't that it's mg times 5 meters. Like it's not going to be force times the 5 meters that you're moving along the path. It's going to be force dot the path that you're moving. So it's only the corresponding, it's only the direction that goes in the same direction as the movement that goes in the same direction as the force. So instead of being mg times 5 meters, it's going to be negative mg times 3 meters minus 0 meters is negative 3 mg times meters. Uh, yeah. So it's only going to be uh the position that you walk up is only going to be, or the position that you're lifting against gravity is going to be the only thing that does work according to this theorem. And also, if you're talking about any type of movement, so you can make this movement still only going to do 3 meters of work. You can make this movement only going to do 3 meters of work. So only by knowing the initial and the final positions, you're able to find the work that's being done just by knowing these initial and final positions. So that's about the most useful thing that you can know without actually doing a worrying about the f dot dr. So without worrying about the uh, derivative or the infinitesimal part, the dr rather than the delta r. So if you want to do something more uh, complicated, so F spring equals negative kx, where x is this displacement from the initial position. So as yeah, we went over this last lecture, but x is just the displacement from the initial position, and that's going to give you this equation where the farther out you are displaced from the initial position, the more force the spring is going to be pulling back uh, and trying to restore itself. So if that's the case, so the work done on a spring or by a spring is equal to F spring dot dr equals negative kx I dot dr equals negative kx times dx. because again, we're only worrying about the motion in the x direction rather than in if it goes, well, in this case, if you do move something, uh if you do move a spring up or down, then that's going to have the same restoring force as if you move it side to side. But we're going to just call whatever direction you're pointing in x, the x direction, and then that's going to give you the values that you want, because you can only move a spring in one direction and it's going to use its restoring force to get back. So if that's the case, uh, then work on the spring is equal to negative k times x squared over 2 from A to B equals negative k over 2 x a b squared minus x a squared. So basically, this is just pointing out that you have to do calculus. You have to actually do calculus in order to get a lot of these answers for work spring and like a lot of other types of forces. But another trick that you can use is you can point out that because it's f dot dr, if because it's f dx, then as you look at the force, uh, the force of a spring is negative k times x. So if you look at the absolute value of the force, it looks like this. And you can find uh, any the work done by looking at the area under this triangle. So looking at this area, which is 1/2 base times height. So 1/2 kx times x. So area 1/2 base times height equals 1/2 x times kx equals 1/2 kx squared. Is going to give you the same values uh, as when you just solve it mathematically, because that is the form that, yeah, because basically that is the form that integrals take. You find the area under the curve in order to find it, and if it's a simple geometric shape like a triangle, then this is going to be just 1/2 kx squared. If you take away part of the triangle, it's going to be 1/2 kx squared minus the smaller triangle. So 1/2 kx squared k xb squared minus xa squared. Area of uh xa goes to xb, let's say. So the area of this under this curve is just going to be the smaller the bigger triangle minus the area of the smaller triangle. So it is again 1/2 k xb squared minus xa squared. So does that make sense?
Yes.
Okay. So again, any force that you're talking about, as you go along the R direction or the X direction, whatever you want to call it, uh, then you can just find the work done by looking at the area under this curve. So would you like me to just do an example of uh, finding work done for an arbitrary function?
Yes.
Okay. So if we take F equals uh, A times X squared in the I direction minus B times Y cubed in the J direction. Yeah. Then we can find the work done by doing F dot dr is going to be equal to A x squared dx minus B y cubed dy. Because it's only talking about the work in the x and y components in it's only talking about the work in the direction that's the same as the force that you're looking at. So in this case, it's going to be A over 3x cubed from xa to xb minus b over 4 y to the fourth from ya to yb. And of course, there are more complicated examples that I could give, especially ones that have uh, values that uh, yeah, values. So you see that y is only in the y component and x is only in the x component. So if you mix those up, then that would make the equation more complicated than it would otherwise be. But as it stands, this is just a over 3 times xb cubed minus xa cubed minus b over 4 y to the b to the fourth minus ya to the fourth, where uh because it's only in that line, you only have to worry about integrating from along those directions along the y and the x direction. So uh now now that we know all about work, let's just set up kinetic energy. So kinetic energy is simply equal to 1/2 mv squared. And what we're going to see is that this change in kinetic energy, this in 1/2 mv squared is going to be the same as the change in kinetic energy is going to be equal to the same thing as the change in the work done on the system. So the way that we prove that is that dW equals m dA or ma dot dr. And this is kind of like not great math, but physicists often use not great math, equals m times dv dt dot dr equals m times dv dot dr dt equals m times v dot dv, which is just going to be m v dv equals 1/2 m times v squared, or 1/2 m times v squared from VA to VB. So 1/2 m VB squared minus VA squared, which is the change in the kinetic energy. So basically, why we care about kinetic energy is because it gives us uh, a measurement of the work that's done on the system without having to worry about actually caring about the work that's the forces that are acting on the system. It just gives us the work, and by setting this equal to the work that we found earlier, so to the work that we found from gravitational energy or from the force done by a spring, we can solve for the velocity as a function of the space or the path that was taken of the work. It's by setting 1/2 mv squared delta v, or delta 1/2 mv squared, equal to the work done by a force on the system. Then we can tell things about the final and initial velocity based on the type of work that was done and the final and initial position, or the path that was taken along when we're talking about friction. So uh, if we're talking about uh, what you may call it, the work done by gravity, so delta K gravity is equal to negative mg h b minus ha, which is equal to negative mg delta y, is equal to m times the acceleration times delta y, right? So 1/2 mv squared, or mv delta v squared, equals ma delta y. So delta v squared equals 2a delta y. So by looking at this, we're able to recover one of the kinematics equations that we've been using just by looking at the kinetic energy and the energy, the work done by gravity. So another thing that I should note is I should just talk about the units of this. kinetic energy has units of m times meters per second squared, or mass times meters per second squared. Not that gets confusing because mass and meters have the same symbol. So kinetic energy has units of mass times energy meters per second squared, which is equal to the units of work, which is the joule. So just doing a sanity check, we see that the work done uh, is of the same units as the work of the changing kinetic energy. So this is why the joule, instead of being generally called the unit of work, is called the unit of energy. And if you have trouble remembering this, then just use the formula E equals mc squared, which is the kinetic energy, or the total energy of a particle in relativistic speeds. So this kinetic energy that we're given, 1/2 mv squared, only works when v is much smaller than the speed of light. But you've seen this equation before. You've seen E equals mc squared. So the units of E equals mc squared are the units of mass times speed squared, because c is the speed of light, which is equal to the joule. So if you need to remember basically what the units of the joule are in terms of your other scientific units, your K, or your masses, your lengths, and your times, then just remember Einstein's equation, E equals mc squared, and that's a pretty easy way to just make sure that you're getting the right values all the time, or you're getting the right units.
Professor,
Yeah.
in the formula for K of gravity, we have a A. Is that just the acceleration of gravity?
So the acceleration of gravity is negative g, right?
Right.
So I had negative mg delta y is the equation for gravity, the kinetic energy for gravity, and the work done by gravity. So when we're talking about just acceleration rather than the particular acceleration that's negative g, then I was just trying to refine the kinematics equation. So it is just a. I went off a little bit on a little bit of a tangent when, yeah, the answer is that it's just the acceleration due to gravity, except negative.
Okay.
Yeah. So since we have this equation, let's do like a kind of standard equation for this type of thing. So, or a standard problem. So you start from, you have a roller coaster, and you start from rest at some top of the roller coaster, go down, make a loop to loop, uh, and then continue going down. So what we want to know is, what is the normal force at the top of this loop to loop? So if we start at some position y initial, or y1, then we can do conservation of energy to find the velocity at that time, and from finding the velocity, we're able to find the centripetal acceleration. So pretend that this loop is more circular than I made it, basically. So we're able to find centripetal acceleration, which means that we're able to find the normal force by doing uh by setting the total forces equal to uh like centripetal acceleration. So at the top of the loop-to-loop, you have two forces, mg and the normal force from the track onto the yeah, you have mg and the normal force from the track uh onto the cart, and then you know from centripetal acceleration from last week or the week before that mv squared over r equals ma pointing down is equal to n plus mg. So v squared, oh, I put a v squared over r squared for some reason. V squared uh at this point at the top of the loop to loop with radius r is equal to r times n plus mg, uh which is interesting. That's good to know, but actually what we're solving for is n, so that was silly of me. So n is equal to negative mg plus mv squared over r, where r is the radius of the loop-to-loop. And then we want to, we know mg, we know r. What we need to know is the velocity at that point. So the way that we find the velocity of that point is to say that 1/2 uh m, or 1/2 m v2 squared minus v1 squared is equal to negative 2g y2 minus y1 is equal to negative 2g times 2r minus y1, because we're measuring y from the base of the loop-to-loop, from the base of the roller coaster. So 2r is going to be the final value because the radius of the loop is 2 times the, or is 1/2 of the diameter, is 1/2 of the height of the loop. So v2 squared and then I put 2g rather than mg because I'm just so used to kinematics equations. V2 squared equals uh v1 squared minus g times 2 times 2r minus y1. So n is equal to negative mg plus m over r times negative g times 2 times 2r minus y1 equals negative or equals plus, and then there is no v1 squared because it starts out from rest, is what I should say. So n equals negative mg times 1 plus 2 times 2r minus y1 over r. And then that should be right. Just a second. Oh, which is equal to mg times 2 y1 minus 2r over r plus r is equal to mg or minus r. Sorry, I'm making a lot of quick algebra mistakes. Mg times 2 y1 minus 5r over r equals mg times y1 over r, or equals 2mg over r times y1 minus 5/2 r. So basically, if you want this equation to work, if you want there to be any sort of normal force, which can only point down, then this equation has to be greater than 0. So y1, in order for this to work, y1 minus 5/2 r must be greater than 0. So y1 must be greater than 5/2 the radius of the coaster. So that is like an interesting question if you're trying to get into roller coaster designs, or if you're trying to think about the minimum requirements for something to be safe, then this is a practical question if you're the type of person who makes this sort of measurement. So let's just save that. And then the last thing we're going to talk about is very basic. We're just going to define power is equal to dw dt. It's just the change in work over the change in time. So this is useful because it just, most things only have a certain amount of power. They can only output a certain amount of energy in the same time. So if you're talking about a bodybuilder versus like a car engine, then both of those can eventually do the same amount of work if you give them enough time, but the engine is going to car engine is going to be able to do the work much faster because it has a much faster power output. So this is equal to F dot dr over dt equals F dot dr dt is equal to F dot v. So yeah, that's the main thing that you need to learn about power. Um, Basically, uh, I didn't write this down or I didn't put this in my Evernote, so I'm going to be doing the equation off the top of my head. But if we have some angle, or we don't even have to worry about the angle, let's just worry about y and x. So if we have a value, or if we have an engine with on a car with a constant power rating E, how much time does it take to get up a hill some distance y, uh given if it's going at a constant velocity, if it's going at its maximum velocity working against gravity. So in this case, work done by the engine is equal to work uh is equal to negative work done by gravity, because the engine is going to, I'm not entirely sure about that negative, but the engine is going to be doing work to cancel out all of the work that's done by gravity. So if they're going uh, at a constant velocity, then the net force is going to be equal to zero. So F equals negative F gravity. So F dot dr engine equals negative F gravity dot dr. So work engine equals negative work gravity. So if this is the case, then the power times delta T equals the work of engine is equal to mg y. So the delta T is equal to mg y over the power of the engine. So that's just how long it's going to take you to get up the hill. If you're going, again, notice that this is independent of the x direction. So if you're going completely, if the angle's really uh, shallow, and you're going the same uh distance y versus this angle, which is less shallow, then you're just going to be going faster, going up this hill, and you're going to travel higher distance, but you're still going to be outputting the same power. So delta T is equal to mgy over the power. So it's only dependent on the y value of work. So yeah, that's kind of interesting, I think. With that, I think that's basically all I have to say about these discussions. Let me check really quickly, honestly, in the check textbook because I uh did this off my the top of my head, whether or not that's right. Uh yeah, it seems right, which I know isn't an answer that you want to say. See, but from my intuition, this seems like a right answer. I was doing it basically just off the top of my head, so it might not be, but do you have any questions about power, work, energy, anything like that?
Professor,
Yeah.
you said that the example that you gave were only focusing on the x direction, or was it the y direction?
Uh, the examples I gave depended on what force directions the forces we're looking at. So, oh, for the work by engine and work by gravity, this assumes that there's no yeah, this assumes that there's no air resistance or anything like that, and it only depends on mgy. So it only depends on the y direction for the work by engine versus work by gravity problem. Actually, I think I saved this, but let's go over a different way to do this if there is air resistance. So if there is air resistance, then there's a maximum V. Yeah, there's a maximum V that can be achieved. So the power is still let me just see this question really quick. 0.75 power equals yeah, power is going to be equal to the force times the velocity. So the power that's going to be fighting gravity is going to be equal to the force mg times velocity, the magnitude of velocity, times sine theta, because that's how much the velocity vector overlaps with the y-axis. So instead of just being this way is actually power dependent, or this way is actually velocity dependent and depends on the grade of the motion or grade of the material. Okay.
So, Professor,
Uh, so this is just another example using maximum value of V uh, that's gotten by there being air resistance as well as gravity. Yeah,
Professor.
yeah.
So this example that you just did is specifically in the case of air resistance.
So specifically in the case of there being some non-conservative force. So honestly, instead of saying all of the power is going to working against gravity, it should be something like 75% of the power. Uh because some of the power is working against air resistance, which is causing it to not be able to output all of the power, output all of the work just working against gravity, and also causing it to uh yeah, causing there to be a maximum value of v, so like a terminal velocity in the v direction or in the direction of movement. So like we said last week, there's like a terminal velocity when you come across or when you come against power, or when you come against some restricting force or some uh, non-conservative force, which is what we call forces that depend on the path rather than just depending on the initial and final positions. Okay. Any other questions before I leave off? This is basically the chapter.
No, Professor.
Okay. Well, I'm going to stop recording and bid everyone adieu.
Bye, Professor.